Hello, everybody. This is Martin. We're going to go ahead and get started here in just about another minute or two. If somebody could raise their hand or send me a message on the chat just to make sure that the audio is going through, I would appreciate that very much. So if you can click the raise hand button. All right, I've got at least a few here. So we'll go ahead and get started here in just another minute or so. Okay, everyone, welcome to a crash course in mixture design of experiments. My name is Martin Bessener, and I'm the president and CTO of StatEase. This is our world premiere of this crash course. So this is the first time we've developed it and are presenting it. Now, of course, a crash course doesn't mean that you're going to be an expert by the end of this 45 or 50-minute presentation, but hopefully it should at least get you started. It should give you a good foundational knowledge, and it should hopefully, hopefully you'll at least know the correct questions to ask if you ever end up using this material in your own work down the road. So I want to thank everyone for coming. We have a good-sized group, and I will just ask one more time, for those of you that can hear me, please click the raise hand button. I just want to make sure that I'm not accidentally muted, or you're not just looking at a muted PowerPoint. So a lot of hand raises here, so I think we're okay to go ahead and get started. Okay, so this is just some little basics here. So because we have a fairly large group, all attendees are muted. You can feel free to send a chat during the presentation. I'll try to periodically check in. If I don't remember, I'll try to reply via email afterwards. If you have any other questions, you can also feel free to contact StatHelp here. Okay. Please provide your company name if you're using Design Expert and the serial number as well. Now, there's going to be a decent amount of material here in the next 45 minutes or so. Don't worry, this presentation, which contains some links and resources and whatnot, will be posted on our website within a few days, and we'll have a recording of this webinar up on YouTube as well. So if you need to leave early or you want to rewatch a part of it, you'll have that opportunity in a few days. And we'll also be periodically doing this crash course as well, maybe every couple months or so. So, feel free to take it as often as you'd like. So just a brief blurb on some StatEase news. Just this Monday, we released version 13. Okay, that's our latest version. And at the very end of this crash course, I will give a very short preview of two features that are very useful for mixture DOE. I'm not going to go through a whole laundry list of feature demos. I just want to point out two things that you may find very useful if you end up using mixture DOE and building mixture designs and analyzing mixture designs in the future. I also want to point out that if you find the material here useful in this crash course, basically we take this 45-minute crash course and we stretch it out to 4 days in our live DOE, live mixture DOE workshop. So you can feel free to check that out if you're interested, if you really want to dive into the gory details. Okay. And that'll also go through software tutorials and a bunch of other stuff. All right, so here's what we'll be doing in this crash course. So first, kind of the goal is to go through some foundational, what is a mixture experiment? You know, a question I often get, I've gotten over, you know, I've been doing this for about 10 years now. Question I always get is, you know, when do I need to use a mixture experiment? What is a mixture DOE? You know, when should I use a mixture versus a two-level factorial design or a response surface central composite design? So that's what we'll talk about in the first part. Afterwards, we'll go through some mixture designs you can use in the future. The third section is kind of a beginner / intermediate, which is more, you know, practical tips and tricks. So, you know, like I said, I've seen tons of things go wrong. I've seen, you know, lots of people make mistakes. And these are kind of the 5 most important ones that I want to, you know, let you know about early so that you don't make them going forward. And then I'll just conclude and give some resources, and, you know, if you want to dig further, some books and other materials you can check out. And finally, at the very end, I just want to show 2 features of Design Expert 13 that are incredibly useful for mixtures. Now, most people are paying annually for Design Expert, and if you are, then you are eligible for a free upgrade to Design Expert 13. That'll be going out at the end of January, but if you want it earlier, you can feel free to contact us. Okay, so what is a mixture experiment? Well, the first thing I'm going to show is what is not a mixture experiment. Okay, this is a very typical experiment, something that, you know, that we run into all the time. Okay, and this is a typical non-mixture experiment. So it looks something like this. So let's say we're baking a cake. You know, this is our cake up here. Okay. You know, maybe we're only varying 2 things, the time in the oven and the temperature in the oven. Okay, so basically what we're doing is, you know, we're blending up a dough batter, and then we're going to put it into the oven at a, you know, pre-specified time and temperature, and then we're going to take it out and we're going to see what the moisture content is of the cake. And what we want to do is we want to hit, you know, at the end of the day, when we're going to be baking these cakes and selling them at our bakery or, you know, wherever, we want them to, you know, kind of on average have a target moisture. Okay, so we could let time go from 20 to 30 minutes and the temperature go from, let's say, 300 to 450 Fahrenheit. Now, here's kind of the thing, you know, the most important thing to realize here about why this is not a mixture. Both of the factors, time and temperature, can be set independently of one another. So let's say I choose a time in the middle of 25 minutes. I can set a temperature that goes anywhere from 300 to 450 degrees Fahrenheit. Okay, so basically my 2 factors are independent of one another. I don't have really any constraints here. I'm obviously not mixing anything as part of the DOE. So this is, you know, a kind of a classic response surface method experiment where I have 2 factors, you know, they go from their low to their high, and I can vary them independently. So here's what a typical response surface DOE designed experiment would look like. You know, you'd have maybe 16 cakes that you need to bake up here. Okay, you know, your first cake, you would put it in at 20 minutes and 395 degrees Fahrenheit, and then you'd go through, you'd do all 16. You'd plug in or type in the moisture content of each of the 16 cakes, and then you'd go ahead and analyze the data. So the DOE, the experimental design plan, looks something like, you know, this is just an example, looks something like this, where the orange dots represent the combinations of time and temperature that you're going to be testing. And notice how here, you know, these points that have little numbers next to them, that means those are replicates, which means you're going to do those more than once. Okay, easy enough. Okay, somebody, yeah, so I'll go ahead. I got a couple questions that I'll talk about here in just a minute. Now, let's take a look at this experiment. Suppose, I love pizza. I love my party pizzas. Here's my pizza right here. Well, let's say we're deciding what cheese we want to put on a pizza. Okay. We could blend together 3 different types of cheeses and put them on top of the pizza. We can use mozzarella, provolone, and white cheddar. Okay. We can, try each cheese on its own. We can try blends of 2 cheeses, or we can try, blends of, all 3 of them. So what we want to do is we want to figure out what's the optimal combination of the, of the 3 cheeses. Each pizza that we cook will have a fixed total of 6 ounces of cheese. So we're not going to be varying the amount of cheese that goes on top of a pizza. We're just going to be kind of varying how we divide out that 6 ounces, how we break down that 6 ounces into, mozzarella, provolone, and white cheddar. So what we'll do is we'll let, kind of each of the cheeses go from 0 to 6 ounces, which that means that, I could look at each of the cheeses on their own. If, for example, mozzarella is 0, provolone is 0, and white cheddar is 6, I could look at blends of 2, or I can look at blends of all 3. But the key here is, this is the most important thing here. Mozzarella plus provolone plus white cheddar equals 6 ounces. Notice this equal sign. Okay, this is called an equality constraint. That means that the things that I'm varying in the experiment have to always add up to the same total. Okay, so somebody asked the question about, why wouldn't you do this as a response surface design with a equality, with a constraint? Well, a response surface design cannot handle an equal constraint. It can only handle a less than or equal to, or a greater than or equal to. So if you're looking at your design plan and it's, you've got columns in it that are always adding up to the same total, you have a mixture experiment. So in this case, what we could do is we can, the responses we measure will be, well, the appearance, does it look nice, or does it look all burnt and crusty? The taste, the texture, do we get soft and oozy cheese versus, hard and chewy, and also cost, we might not want to use up a lot of the most expensive cheese. So now notice that here, the components of the cheese blend cannot be set independently of one another. Okay, this is a key point. If I put in 2 ounces of mozzarella cheese, okay, that means I have to put in 4 ounces of the other 4 total ounces of the other 2 cheeses into the blend. So this is a typical mixture experiment. Why? Because again, as part of the experiment, I have this equality constraint here. Okay. If you ever have a constraint that looks something like this, where, A plus B needs to be, less than or equal to 2, okay, if that's your only constraint, you don't have a mixture experiment. You have to have this equal constraint here. Okay. All right, so that was one question that had come in. Okay. All right, so a typical mixture DOE, when you go through and you build it, would look something like this in this situation. So you'd have your 3 components. Okay. You'd have your 3 components here. And each one, if you go through each of the blends that we're going to be testing, they all add up to 6. Okay, so notice how in the first run you have basically a 50-50 blend of provolone and white cheddar. In run number 2 here, you have most mozzarella, but a little bit of provolone and white cheddar. So you go through and you can take a look, do each of these, bake each of these pizzas, collect the 4 responses here, type them in, and analyze the data. So once again, the key take-home message here is sum of the 3 cheeses equals 6 in each run. Okay. Typically, when you're varying, proportions, or you're varying a percentage, whether it's a volume percent or weight percent, and it all adds up to this, 100%, where the proportion adds up to 1, that's also another sign that you have a mixture experiment. Okay, but that's really just the scale change, and it's not really a meaningful change from a DOE perspective. So here's what, if you actually go through and you plot this experiment that I put here, okay, if you actually go through and plot it in the 3D space, what runs you're going to be testing, this is what it looks like here on the right, on the left-hand side. It's not very easy to see in 3D, but you'll notice that all of the points lie along a triangle, okay, that on the right side I kind of drew in so that you could more clearly see where all the points are lying. So notice how really this is a two-dimensional problem, even though we have three components. The reason why is because, once we know how much of the first two cheeses we're putting in, the third cheese, the amount that's going in is fixed because it needs to add up to 6 in this situation. Okay. So what I could do is I could basically take this triangle, also known as a simplex, and just flatten it so I could see it a lot easier. And this is what the DOE looks like. So if you look at DOEs of mixture experiments, you're going to see something that looks like this. Okay, so the vertices here would be the one cheese blends, so each cheese on its own. The edges in this case, like this red one, are represent blends of 2 cheeses. Anything in the interior represents blends of all 3 cheeses. And notice once again that if you if you have a little number next to the point, that means you're going to be doing independent replicates there. Okay. So if you've ever seen these simplex diagrams, this is what it all means. Okay. So identifying a mixture experiment. This is the the last point on mixture DOE basics. So blending experiments should usually be set up as a mixture DOE, but not necessarily always. If you're, once again, the key thing to look for is the equality constraint. A lot of times people will come to me and say, hey, I'm varying the concentrations, okay, or I'm varying the amounts of the components, okay, because maybe it makes more sense to do that. Maybe the amount is important. Well, in that case, you may have a response surface experiment, because if you go through each run, the total concentration of A plus B plus C plus D usually doesn't need to add up to a fixed total. If you're varying the weight percent, the volume percent, the proportion of the total, or if you're varying the amount, but the amount always adds up to a fixed total, you have a mixture experiment. Okay. All right. So the key to verifying whether you need a mixture design is to determine if any of the columns in the design plan add up to a fixed total. Okay. Once again. And I'm still getting questions on people trying to force this into a response surface design. Don't do that. And I'll talk about in the tips and tricks section on why that's a really not good idea. Okay, because I see this all the time where people really don't want to learn mixtures. They don't feel comfortable. And by and I'm not talking about somebody that doesn't have any statistics training. I've seen people with master's degrees in statistics try to avoid mixture DOE because they don't want to learn it. It's kind of insane to me, but that's the world we live in, and hope that's why we're giving this a crash course. And one thing I want to point out is that sometimes you may have an experiment where part of it is a mixture. Okay, so you might have like a cake formulation. Okay, but you may also have non-mixture factors as well, like the temperature of the oven. Okay, so you might have a formulation, but you might also have some process. This is called a mixture process combined design. It's still basically a mixture design, but not it's not a pure mixture design. There's also some external factors outside of the mixture as well. All right, so that hopefully you know now kind of when what to look for when you're deciding between a mixture DOE and a response surface or a factorial DOE. Now I'm going to talk about some of the types of mixture designs that you can use. Really, we're only going to be talking about the optimal computer generated designs, and I'll go through an example from beginning to end to show you how this would be done. So there are basically 2 categories of mixture DOEs. There's simplex-based designs, which we also call canned designs, because they're essentially prepackaged designs you take off the shelf and you use. There are also optimal custom computer generated designs. In practice, 98, 99% of the designs I use are these optimal designs due to their flexibility. Okay. I'll just talk a little bit about canned designs here, just so you know when to recognize them. So simplex designs are canned and straightforward, as I said. However, in order to use a simplex design, which are these nice triangular designs, one of the following conditions have to hold true. So either all components go from 0 to 100%, or all components have the same range, which is, that this first point is really just a special case of the second one. And simplex designs look something like this. There are these triangular designs where everything goes from 0 to 100, or everything has the same range. This is 3 components here. This is 4 components here. And you can see that the points are nicely spaced and symmetric and whatnot. Okay. So textbooks will often start with these designs, which I find to be pretty useless for the most part. I find them to be incredibly restrictive and limited purpose. Okay, because in the real world, it rarely makes sense for all components to go from 0 to 100% of the mixture. Okay, so if you're making bread dough, I mean, does it make sense that yeast is 100% of the formulation? Would it make sense to test the formulation of 100% yeast or 100% butter? No. Similarly, 0% yeast is probably not going to be, something that you want to test either, because you're not going to be making a very nice bread. And it's also, in my experience, somewhat rare that each component has the same range. So that means, you might have a component that goes from 2 to 5, and one that goes from 97 to 100, and so on. It's pretty, I see it pretty rarely. And one kind of, tip is, don't force I've seen this happen occasionally, is some people, because they want to use a simplex design, this nice triangular design, don't reduce all of your components to have the same range so that you can use a simplex design. I've seen this time and time again. Just wait one more slide and we'll talk about optimal designs. Okay, so as I say here, a better option is an optimal computer generated design, which I'll be talking about here in just a second. If you do want to use simplex designs in Design Expert, when you open up a new design, this is where you would go here. You would go to the mixture section and then click Simplex Lattice. Optimal design. This is where we're going to be spending pretty much the rest of the crash course. This is a more realistic example. Let's suppose you have the following set of constraints. Okay, you have, component A goes from 0 to 20%, component B goes from 0 to 50%, component C goes from 0 to 50%. However, A and B, the total of those two needs to be at least 10%. Okay, so I can't have A and B both be 0% in any of the blends. So that's called a multi-component constraint. Also, I have a ratio constraint that says the ratio of B to C needs to be between 1 and 1.5. So that means I always need more B than C inside of my blends. Okay, but I don't want too much more of B. So the ratio is capped at 1.5. And then finally, of course, I have the equality constraint here that A plus B plus C equals 100%. This is a much more realistic example of what, of something that I would see. And in Design Expert, or, in any software, you would set it up like this. Here's the key again. The only difference between response surface and mixture DOEs in setting them up in Design Expert is whether or not there's a total field, meaning every run needs to have the same total. So you would go through, you'd set up your 3 components, your lows and highs, and then you can click on this Edit Constraints button and put in, A plus B needs to be greater than 10, and the ratio of B to C needs to be between 1 and 1.5. So this is an example of an optimal design. Okay, so notice here's what the actual mixture experimental design space looks like. This big triangle here represents, kind of the 0 to 100% space. Okay, this white region here, right here, is where we're going to be experimenting. That's all that's left over after I take into account all of my constraints. okay? Doesn't really look like a so if I, Detective Dan over here, zooms in on this little white region here, I basically get this here, this right triangle, the triangle on the right side here, okay? So notice here how if I really wanted a simplex lattice design, I'd have to basically just do something like this, which is useless. So you could see that my space is really, really oddly shaped. And this is incredibly common. Using a triangular design here ain't gonna work. So not a great fit for simplex design. And like I said, this is more of the usual, this is more of the norm rather than an exception. So here's what an optimal computer generated design looks like for this complicated design space. So what I would do is I'd define my design space here. I use Design Expert version 13, and I'm going to show you how to do this here in just a minute. To basically say, here is my set of constraints. Here are my components. Here's how many runs I want to do. Build the best design for me possible. And then Design Expert would say, okay, here are the runs you should do. So it would have, blends in the interior, blends on the edges, some blends at vertices. Some of the blends would be done more than once, like this one. And this would be the DOE here. This you could only get by using optimal custom designs. All right, so if you wanted to actually go through this in Design Expert, here's a little preview, and then I'm actually going to switch to a software demo. Optimal designs are actually very straightforward to build. So first, you just need to choose the components, set the lower and upper bounds, and then add any constraints that involve more than one component. And you may not have constraints that involve more than one component. So in your, in Design Expert, you would go to, New Design and then select Optimal Custom. And then here, you would put in the total and any constraints involving more than one component, you'd use this Edit Constraints button here. And then type in your lows and highs here, and you're 50% of the way done. Somebody asked if this is only with V13. No, this can be done in version 12 and 11 as well. Next, choose the design size, meaning the number of runs. What types of runs you want to do? For example, do you want to do some, replicates? Do you want to, do you want to plug in any big gaps in the space? You might also need to choose blocks. For example, if you can't do the experiment all on one day. And finally, what model order you're interested in fitting. So are you interested in, fitting a straight line and interested in fitting a quadratic curved surface and so on. That's set right here. Okay, so this is, like I said, a crash course, so we can only talk so much on each of these things here, but really the key take-home message here is that the defaults are what we recommend in most cases. And once you set this, you're basically done. The Design Expert will generate the design for you. Okay, so this is a 20-run design here. All right, so what we're going to do now is I'm going to switch over to the software for 5 or 10 minutes, and I'm going to go ahead and show you how to actually build a design, an optimal mixture design, how we would analyze the data and build a model, and finally optimize the formulation. Again, this is going to be incredibly quick, and we're going to go back to the pizza cheese blend example and use the following components and bounds. So we're going to let mozzarella now go from 2 to 6 ounces, provolone go from 1 to 4 ounces, and white cheddar go from 0 to 2 ounces. This is an actual experiment that I did years ago, and these are the bounds that I used, mostly because white cheddar of 6 ounces was not very good. So I capped that at 2 ounces. But the total cheese is 6 ounces, so I'm not varying the amount of cheese I'm putting on. I'm keeping that at 6 ounces. I'm just changing the composition of the cheeses. All right, so let me just let me get out of let me see here. Let me open up Design Expert here. So hopefully you're able to see Design Expert. So I fire up Design Expert. Okay, I'm going to click on New Design. I'm going to go ahead and click on mixture. I'm going to do optimal. Now, if you start setting this up as a simplex lattice design and it's not a simplex, triangular space, the program would warn you and tell you to use an optimal design. I have 3 components. That's what I always set first. Now my total is 6 ounces. Okay, so Design Expert's going to give me runs that add up to 6. And I have 3 cheeses. I have mozzarella, which goes from 2 through 2 through 6. Okay, just go ahead and 2 through 6, and then I have provolone, which goes from 1 to 4 ounces, and then I have white cheddar, which goes from 0 to 2 ounces here. Okay, if I had any multi-component constraints, so for example, like if I wanted, total of white cheddar plus mozzarella to be at least 3, I would click on this edit constraints button here. But I don't have any of those here for the sake of simplicity. I'm going to go ahead and click next. Now what Design Expert is going to say is, it's going to check all of these bounds and say, I can't have 6 ounces of mozzarella if I have to have at least 1 ounce of provolone. So Design Expert will check the ranges and offer to adjust them for you. If you like what you see, you can click OK. If not, you're going to have to go in and manually edit these. So it's typically going to reduce the upper bounds first. If you don't like that, if you don't want mozzarella to have an upper bound of 5 like it's suggesting here, you would need to go through and manually set the provolone lower limit to 0. But I'm going to click OK because I like this. And then here is where I would select how many runs I want to do, what types of runs. And unfortunately, in 50 minutes, we can't go through all the details here, but the key take-home message is that I start with a 16 run design. That's the suggestion by Design Expert. Blocks are here, and there's a bunch of other options that we just don't have time to go through. And then finally, what I'm going to do is I'm going to enter the response information. I'm only going to look at taste here. And then if I go ahead and click finish, Design Expert will build a design for me. Now I would go through, I'd have to make 16 pizzas. I'd have to see how tasty each of the cheese blends are and go from there. Now, here's a little thing to keep in mind. Sometimes you'll get things like, let me zoom in a little bit here. Run number 2 says I need to use 2.70582 ounces of mozzarella cheese. I don't have a scale that can measure out that far, okay? In Design Expert 13, there's a new feature called round components or round columns, which is right here. I can click on it, select mixture 1, and say, you know what, I could round off to 1 decimal place, or I can round off to 2 decimal places. Click OK. And what Design Expert does is it now rounds off to the precision that I selected. So now I don't need to go through and do this manually. I can now do my experiment, in a feasible way. So this is new to version 13 here. I already collected the data here, so I'm going to go ahead and just open up the file that has the responses in it. Now this was a score from, I believe it went from 0 to 200. And what I'm going to do is just do a very quick analysis here. So I start with the fit summary, which suggests a quadratic model, meaning there's nonlinear blending, there's curvature going on in my system. I could look at the model fit. I see that, if I start with the full quadratic model, the linear mixture is significant. Cheeses A and B, which are provolone and mozzarella, are blending together non-linearly, as are cheeses A and C. Cheese B and C is kind of borderline, okay, with a p-value of 0.14. I don't have any issues with lack of fit. All of my R-squared values look really good. Okay. So what I'm going to do is I'll take out this BC nonlinear blending term just to make the model a little simpler. I don't think it's really going to make any big changes here. So you could see here, this is the result. This is what I'm dealing with here. Here's what my model is telling me. My model is telling me is that the best blends are right around here. So high white cheddar. Now, if I look at the real contour plot, what this does here, let me go ahead and turn off the design points here so it's a little bit easier to see. Notice here how I kind of have a, you know, a situation that's not ideal because I have this red region. Again, this gray area here is my entire mixture space. It looks like maybe if I had made the triangle a little bigger, I could have perhaps, you know, gotten a little bit of a better response, maybe somewhere in this region here. Hopefully you can see that if I pushed out this red region a little further, but that's about where I can go. I can use numerical optimization to maximize the taste, stretching out this upper bound a little bit. And the first solution I get is mozzarella, 3.73 ounces, provolone, 1 ounce, white cheddar, 1.23 ounces. So it looks like maybe if I let, you know, provolone go a little bit lower, you know, maybe I chose a lower bound of 0 instead of 1, perhaps I could have gotten a slightly better, slightly more optimal result. And I'm expected to get a taste of 208 out there. Okay, so you can see that on the 3D surface as well. You can see that clearly what's going on here. All right. So that was, as I said, a very quick, that was a very quick demo, but hopefully, you know, it at least gives you a flavor, so to speak, of how this process works. All right, so now for those of you that have done some mixture experiments or who, you know, who maybe find all of this to be really easy, here are some tips and tricks that I like to, you know, kind of some practical guidance I like to give, you know, at the very beginning so that people learn to do this the right way. So first of all, don't use factorial designs. If you have a mixture problem, don't, and I'll show an example of this here in just a second, don't try to basically find a way to make factorials work. The second tip I have is, this I see fairly frequently, and like I said, a lot of times I see this by statisticians because, you know, to them it's all math. Don't convert to ratios. So sometimes people try to be sneaky and they'll say, I love my response surface designs and I can use one if instead of looking at mixture components, I look at ratios. I really dislike that approach, unless, you know, there's some scientific reason that, you know, you really only care about the ratios. If you're looking at mixture components, I really dislike, you know, changing the problem to a ratio scale, unless there's some, you know, scientific reason that it makes more sense to look at ratios than individual components. Spend the most of your time on choosing the components and the ranges. Experiment iteratively, especially if you have new problems. You don't necessarily need to do, you know, a one-shot approach. And this is another new feature of version 13 that makes, you know, that I'll show it to you, that makes this so much easier. And finally, master building optimal design. So in other words, take, you know, 30 minutes, and that's really, I think, all it takes to get a good foundation on how to set up these optimal computer-generated designs. That's going to pay huge dividends going forward. So I'll talk about these one by one here in the next 10 minutes or so. This is something I see all the time in textbooks, and I just don't understand really why. So we often have a situation like this. You know, you have components A, B, and C going from 0 to 10%. Component D is what we call a filler. So maybe it's water. Maybe if you're making tablets, it's sugar. It's basically just used to bring the total up to 100%. It's supposedly an inactive or inert substance, but sometimes, you know, people have gotten burned by that. So what textbooks or other people will suggest is often ignoring component D and doing a 2 to the 3 factorial design on components A, B, and C. Okay, and the reason why you can do this mathematically is because components A, B, and C, if they both If all of them are at 10%, then the filler would be 70%, so you get 100%. Two major issues. The design is poor. First of all, you're only going to be looking at extremes of components A, B, and C. You're only going to be testing 0 and 10%. Second of all, if it turns out that the filler actually does have some effect, the factorial model is going to be misleading. Okay, so I really dislike this approach. I still don't understand why a lot of times mixture courses will start with this, saying, hey, you can use this. So here's what, in this situation, here's what a 4-component optimal design looks like. It's 10 blends that we're doing. And notice here how I have, component A, some of the values are 0, some of the values are 10. Sometimes it'll take, 3.6 and 5.6 and whatnot. So you could see that, for 10 runs, I could basically get a full quadratic model here. If I did this factorial design ignoring the filler component approach, I'd still have to do 8 runs, but all I'm getting, I'm looking at the extremes of 0 to 10. I'm ignoring anything involving D. So if there's really something going on with D, it's gonna get lumped into the effects of A, B, and C. So really, I'm basically saving 2 runs to use a familiar design that's incredibly, that's very poor compared to a 10-run mixture design. Okay. So this is why I really don't like to use factorial designs for mixture data. If you have a mixture, just use a mixture, use a mixture DOE. Okay. As you can see, there's really not a ton of information. Like I said, this is not, I'm just not going to talk about it anymore. Hopefully this gets the point across, but this factorial design can only fit basically a flat line to your data. This mixture design here can fit a curved surface that tells you, how your components are interacting with one another. Are they blending together linearly or non-linearly? The factorial design can only look at linear effects, and it has to, and the fact that D, the filler component, is inactive is critical. Otherwise, that effect is going to be mushed in with your other 3 components. So don't do this. That's my first. And this next tip is something that's somewhat related to this. I see this fairly frequently. Don't use ratios. So if you have 4 components, don't use 3 ratios so that you could use a central composite design. So don't use ratios so that you can use factorial or response surface design. So to avoid using mixture DOE and to overcome the limitations of the factorial designs that I talked about, experimenters, and I'll say sometimes even I've seen, people, like I said, with master's degrees in statistics say, you know what, I'm just going to convert this mixture problem to a ratio problem, and I'm just going to use my, my classic canned response surface design. So the way that this works is, let's say you have components A, B, and C. Sometimes what people do is they'll say, you know what, I'm gonna look at the ratio of A to C, and I'm gonna look at the ratio of B to C, and I'm gonna do a 2-factor, response surface design, and that's gonna get, I'm gonna be free and clear. First of all, notice that if any of your if all of your components have a lower bound of 0, this approach doesn't work because you can't put a 0 in the denominator, and the whole problem just falls apart in that situation. So there's one reason why you shouldn't do it. Okay, but in my experience, this is a bad idea unless scientifically it really, you only care about the ratios. In that situation, you have to let the subject matter knowledge guide what you're going to be doing. But I'm talking about starting with a true mixture problem and reframing it as a ratio problem. I don't like it for the following reasons. This approach produces poor designs in the original mixture space. So if you actually try building a ratio design, convert to ratios, use a central composite design, and then see what it looks like in the mixture space, it's going to be very poor. And I don't have time to go through all the details here or show too many examples, but you're going to see it fills the space very poorly. It's asymmetrical, very poor design properties. I also find it to be incredibly tedious, okay, because you need to convert to ratios, then do the DOE on the ratios, then convert back, to mixture components. And once again, it can produce models that are misleading. So I don't like using ratios unless you have a really good reason to do so. Tip number 3, spend a lot of time choosing the components and ranges. So as I said before, the first step in any mixture experiment is choosing what components you're going to be blending, and what the upper and lower bounds of each component will be. In my experience, this step is actually absolutely critical. Most of the failures that I see, and by failure I mean you get a DOE that doesn't give you any results, is due to choosing wrong mixture components and/or the wrong bounds. Bounds are usually chosen with subject matter knowledge, historical data, and sometimes just guessing. The next tip I tell you, number 4, is going to be kind of a way to get around this and possibly mitigate the chances that you're going to screw up. And in mixtures, it's trickier because if you want to put in more of one component, you've got to put in less of another component. If you want to reduce another component, you've got to make it up by putting in more of another component. So in mixtures, this problem is way harder than in response surface designs or in factorial designs. And here's what ends up happening a lot of times is what I see. Let's say this is the triangle of truth. And what often happens is people will take a guess and say, you know what, I'm going to experiment in this green region here, and they're discouraged because once they collect the data and they do the analysis and optimize, they get basically nothing. It looks like nothing is significant. And what really should have happened is they should have experimented here, because this is where all the action is happening in their process. So this is just an illustration of what usually happens. Now, tip number 4 is kind of related to this. It's saying experiment iteratively. So in other words, if you do take a guess and say, okay, you know what, I experiment here, don't use up all of your budget, because maybe you could save some runs to perhaps expand your space out a little bit. So consider an iterative approach. This is tip number 4. Design of experiments, it's often presented as a one-shot approach in textbooks, meaning all the textbooks I've seen say, okay, choose your factors or components, size the design, build the design, analyze, and then next problem or next section. I don't like this. This is, again, the textbook approach. In my experience, it's often wasteful, and a lot of times people aren't even aware that you could do this adaptively and iteratively. So here's an example of this. So instead of depleting your entire run budget on the first pass of the experiment, use a fraction of the runs and leave some behind. After analyzing the data, and optimizing, you can choose what to do with the remaining runs. Now, this of course assumes that you can go back and experiment again, and that you have sufficient budget to leave some runs kind of on the side. Here's what you can do kind of on the second attempt. You could expand the mixture space and put the remaining budget in the new area to better optimize the process. Maybe you might want to shrink this mixture space and put the remaining runs in a smaller area where you want more precision. Maybe you fit a quadratic model, but you want to, it turns out you need to fit a cubic model, and you can, use the remaining budget for that. Maybe you might want to maintain the original design space and put the remaining, use the remaining runs to fill the large gaps. So there's a multitude of things that you can do. And this is very easy to do in Design Expert 13. This is another feature. You could click on this Augment Design button, and there's a thing called Modify Design Space here, where basically it'll say, do you want to expand your space? Do you want to shrink the space? Do you want to shift it over? You could either choose to keep your original data if you want, and then simply add more runs to kind of the reshaped region. Okay, so Design Expert 13 makes this very easy to do. And here's a free YouTube video of a webinar that we did just on sequential experimentation. So if this kind of, if you're interested in it, it sounds useful, feel free to check out, this is a 1-hour free YouTube webinar that we did that gives that goes into a lot more information on this. And finally, master building optimal computer generated designs. So most of the designs you'll build will be optimal computer generated designs. Even in situations where a canned simplex design can be used, an optimal design might still have better properties. So learning the ins and outs of these designs, in my experience, will pay huge dividends going forward. So here's a tutorial, a free tutorial on building and analyzing an optimal mixture design. This is a tutorial here on using optimal design. So this is more advanced. And finally, if you want to, spend 2 to 3 to 4 days on just learning the ins and outs on how to use the software and going through it, you could consider attending a StatEase mixture DOE workshop. Our next one is at the end of January. So, conclusion. Mixture DOE is a very powerful tool that unfortunately does not receive much attention, and in fact sometimes people try to actively avoid it because it's a new, statistically it's a new thing. It's not taught in college, it's not taught in kind of statistics DOE classes because it's really kind of a formulation specific thing. Design Expert software contains all the latest and greatest tools for building and analyzing mixture experiments. The key to recognizing a mixture experiment is determining whether or not there is an equality constraint. Again, this is what's gonna make or break it. And if you enjoyed this presentation and found it useful, consider taking our 4-day distance-based workshop that dives into great detail on all the topics I discussed and actually teaches you how to use the software. All right, so what I'm going to do now, and here are some resources you can use. Okay, this is kind of the Bible of mixture DOE. This is the Cornell textbook. Very theoretical, very technical. This is a book that we co-wrote at StatEase, which is more geared for engineers. And then finally, if you want to, take a workshop, here's the little blurb here. So now what I'm going to do is I'm going to go through the questions here. So I see lots of people submitted questions. So for example, we got a question here about rounding. Is there a way to evaluate a design after rounding? Okay, so if you use the rounding feature, is there a way to evaluate it? And the answer is yes. You need to go to the you can basically look at the design evaluation before and after the rounding, and you can see there's a ton of statistics there that tell you, kind of how good, and for some reason I can't get out of presentation mode here. So, but the answer is yes. Another question is, can you add points to an already made design? The answer is yes. You can click on that augment design button and it'll ask you, do you want to add additional runs? Do you want to modify the design space and then add additional runs? So the answer is yes. And then somebody asked about YouTube links. This presentation will be up in a day or two, and the links are directly inside this document, so you can click on them. You can also go to our YouTube. If you just type StatEase into YouTube, you should get our channel, and it's got all the presentations there. So if you want to, get on it today during your lunch break, you can check out our YouTube channel. So that I think takes care of pretty much all the questions. Now what I'm going to do is I'm going to just, okay, there was a little pop-up here. So I'm just going to do a 2-slide preview of Design Expert 13. And I actually already mostly talked about these. So again, Design Expert 13 was just released on Monday. The 2 features that are really the most useful for mixtures are the Modify Design Space wizard and the round columns feature. So these are the only ones I'm going to talk about here. We also have Poisson regression, multiple analyses, a bunch of other things in here, but for the sake of time, I'm just going to talk about the ones that are most useful for mixtures. So somebody asked about adding points to an existing design, or this is what the augment design button, which is new, is going to do here. You could select modify design space and it'll even give you a little graphic. It'll say, here's the original design space. Here's what you can do. You can either shrink the space, you could expand the space, or what you could do is you could simply shift the space based on the results of your first DOE. And then what you could do is you could add, hopefully if you have a little bit more run budget left over, you could add the runs, they'll basically be added to this remaining space here. So this is very common. A lot of times when people do DOEs and they optimize, they get an optimal solution that's right on an edge or right at a vertex. What this allows you to do is basically move the space over just a little bit, add a few more runs, and see if you can do better. Okay. So I got a question about the augment. So if a person can augment the design, let me see here, for some reason, is there a downside to adding the runs later? Generally, no. Sometimes people will, well, I guess the downside is that the first pass of the experiment will have fewer runs. So there will be less precision or power on the first time through. Sometimes people will also add a second block, also block the first and second part of the experiment, which does require basically one additional run. So that is, that would be a downside there. So this is the modified design space wizard. Okay, I got a question here. How many replicates do we need to run? Typically, we recommend a minimum of 3. That's kind of the, a good bang for the buck. We generally, we start with 5, and generally more than 5, you don't get too much benefit beyond that. So I'd say between 3 and 5 is kind of the answer that works in, 98% of cases. Somebody asks also about, can we use formulations and process factors together in a mixture design? The answer is yes. You need to build it. You need to build it optimally. There's really no canned designs for that, and unfortunately, we just don't have the time in this crash course to talk about it. But we do talk about that in our workshop and in those YouTube links that I put in there. And then the second feature I talked about already is this round columns button, which, let's say you get a design that looks like this. You can now round it off to something that looks like this, and Design Expert will maintain the equality constraint. So you don't have to, it's very tedious to do this by hand. Okay. Got another question. Is there more power to doing it all up front or adding strategically later with the augment? Yeah, so typically we would be talking about precision. Yes, there is typically, it's a good question. There is a trade-off. If you have, it's almost like a mixture. What percent of your runs are you going to do in the first pass? What percent of your runs are you going to do in the second pass? I mean, that in itself is a mixture because you have the runs have to add up to your total budget. Typically, if I have to do a bare minimum, if my first pass is very poor, meaning, I can't do any replicates, I can't, if to save a few runs, I have to forego replicates and space filling points, I would typically just do it as one shot. If I can build a decent first design and then, I still have, another 10 to 20% doing it later, then I would go with a two-step approach. It's very, so Bill, it's very, it's kind of tough to, it's very problem specific, and it's really, it's hard to give a super general answer because you kind of have to see, okay, what's your budget? What am I expecting? But in general, if I can get a decent first design using 80% of my budget, then I would save 20% for later. That's kind of like a rule of thumb that I would say works, 75% of the time. But a lot of it really does require looking at, kind of making a judgment call with a specific problem. So I want to thank everybody for attending the very first mixture crash course. Hopefully you at least are aware of the types, when to use a mixture DOE. What an analysis looks like, maybe some tips and tricks on, kind of to get you started. So we're not expecting experts at the end of a 50-minute crash course, but hopefully you at least know the right questions to ask. So from here on out, if you have any questions, you could feel free to email me, or you could send them to that StatHelp email address. So it was stathealp@statease.com. And we'll, over the next day or two, we'll try to get back to you to help you get started. So once again, thanks for attending. Have a good day. Good luck in all of your future work, and we'll hopefully see you later. So thanks again. Bye-bye.